Now, welcome to lecture of vapor compression refrigeration cycle. This cycle is the hero behind your refrigerator, air conditioner, and even industrial cooling systems. It's a thermodynamic cycle that uses work to move heat from a cold space to a warmer one, defining the natural or deviation from the natural flow of heat. Think about your kitchen fridge. It keeps food cold by absorbing heat inside and dumping it outside, all thanks to this cycle. Today we will explore how vapor compression refrigeration cycle works. We will see its component and why it's so widely used. You will learn about the compressor, condenser, expansion valve, and evaporator, and how they team up to create cooling magic. We will also analyze the cycle using thermodynamic tools like the TS diagram, which shows heat transfer and efficiency. A key metric we will cover is the coefficient of performance or COP, which tells us how efficiently the cycle cools. Beyond mechanics, we will discuss the real-world applications from freezers to heat pumps and touch on challenges like environmental impacts of refrigerants. For example, older refrigerants like CFCs harm the ozone layer, pushing engineers to find greener alternatives. By the end of this lecture, you will understand why vapor compression refrigeration cycle is a cornerstone of modern comfort and industry, and how it's evolving to be more sustainable. This builds on our prior discussion of cycles like Otto and Breton. But here's we are flipping the script to focus on the heat transfer instead of work outputs. So let's see the vapor compression refrigeration cycle. Now we will start with the basics of vapor compression refrigeration cycle. This cycle is the heart of most cooling systems, from the refrigerator in your kitchen to massive industrial chillers. What is its job? Its job is to transfer heat from a low temperature area, like inside a freezer, to a high temperature environment, like your room, using a refrigerant as the working fluid. Unlike the power cycle that produce work, vapor compression refrigeration cycle consume work to move heat, making it essential for refrigeration and air conditioning. The cycle involves four key components: a compressor, condenser, expansion valve, and evaporator, which we will explore in detail. The refrigerant flows through this, changing from liquid to vapor and coming back, absorbing heat in one place and releasing it into another place. Picture your air conditioner. It cools your home by pulling the heat out and dumping it outwards. The vapor compression refrigeration cycle is highly efficient and versatile, operating over a wide range of temperatures, which is why it is used everywhere, from your cars to the skyscrapers. We will analyze it using thermodynamic principles, like those that we have seen in the previous lecture, focusing on the process like isentropic compression and isentropic expansion. A key measure is the COP, which compares the cooling output to energy input. A higher COP means better efficiency. For example, a modern refrigerator might achieve a coefficient of performance of 3 delivering 3 times the cooling energy it consumes. Today, we will also touch on environmental challenges like finding eco-friendly refrigerants to replace the harmful CFCs. Understanding VCRS or the vapor compression refrigeration cycle opens the door to optimize the systems that keeps us comfortable and preserve food. Now let's move to the component and see how these cycles come together. Now let's meet the important components of vapor compression refrigeration cycle. Its 4 main components. First, the compressor. This is the cycle's powerhouse, taking low pressure refrigerant vapor and compressing it into a high pressure, high temperature vapor. It's like squeezing a balloon to heat it up. The work goes in to boost the refrigerant's energy. Next, the condenser. Here, the hot high pressure vapor releases its heat to the surrounding, like air or water outside your refrigerator. As it cools, the refrigerant condenses into a high pressure liquid ready for the next step. Think of the condenser as the heat dumping radiator on the back of your refrigerator. Third, the expansion valve or the throttle valve. This clever device drops the pressure of the liquid refrigerant suddenly, cooling it down into a low pressure, low temperature mix of liquid and vapor. It's like popping a soda can, a pressure drops and things gets chilly. Finally, the evaporator. This is where the magic happens. The cold refrigerant absorbs the heat from the surrounding like the inside of your freezer, causing it to evaporate back into a low pressure vapor. That heat absorption is what keeps your uh, food frozen. These components work in harmony with the refrigerant cycling through the phase change to move heat efficiently. Each play a specific thermodynamic role, which we will analyze later with diagrams. For now, picture your air conditioner just like the evaporator cools your room while the condenser dumps the heat outside. Understanding these parts is key to grasping how vapor compression refrigeration cycle delivers cooling. Next, we will walk through the process flow to see how they connect in action. Now we will follow refrigerant journey through the vapor compression refrigeration cycle. Now we will go through step by step. Consider step number 1, that is compression. Low pressure, low temperature refrigerant enters the compressor as a saturated vapor. The compressor squeezes it isentropically, meaning constant entropy, into a high pressure, high temperature superheated vapor. This process adds work heating the refrigerant like pumping air into a tire. Coming on step number 2, that is condensation. The hot vapor flows into the condenser where it releases heat to the surrounding, like air outside your refrigerator. This happens at constant pressure, cooling the refrigerant until it condenses into a high pressure liquid. Imagine steam turning back to water on a cold window. That's condensation. Third is the expansion. The liquid refrigerant heats the expansion wall where the pressure drops abruptly. This isenthalpy process, no heat is added or lost, causes the flash evaporation, turning the refrigerant into a cold, low pressure mix of liquid and vapor. It's like spraying an aerosol can where the sudden pressure drops fills the contents. Step number 4, that is evaporation. In the evaporator, the cold refrigerant absorbs the heat from the surrounding, like inside of your freezer. This constant process vaporizes the refrigerant completely, turning it back into low pressure vapor. That heat absorption is what cools your food. The vapor then turns to the compressor and the cycle repeats. Now here we can see the evaporator cools the room while the condenser dumps the heat outside, just like the air conditioner. Now here the each step precise the thermodynamic change which we will visualize next in the TS diagram. Understanding this flow shows why vapor compression refrigeration cycle is so effective at moving heat. Now let's move on analyzing this process thermodynamically. Now we will see vapor compression refrigeration cycle using a temperature and entropy or TS diagram. It's like a roadmap for the cycle's energy flow. First, consider the compression process 1 to 2. The refrigerant undergoes isentropic compression in the compressor, meaning entropy stays constant. The temperature and the pressure rises, turning low pressure vapor into hot, high pressure superheated vapor. This is the work input stage, like pedaling a bike uphill. The second is condensation, which is 2 to 3. In the condenser, the refrigerant rejects heat to the surrounding at constant pressure. It cools from superheated vapor to a high pressure liquid, losing the latent heat. On the TS diagram, this is a horizontal line showing the heat loss. Third is the expansion, 3 to 4. The liquid passes through the expansion wall, undergoing isenthalpic expansion, and the enthalpy stays constant. Pressure and temperature drops sharply, creating a cold liquid vapor mix. This step is like a quick descent, setting up the cooling phase. The fourth is the evaporation from 4 to 1. In the evaporator, the refrigerant absorbs heat at constant pressure, vaporizing completely into low pressure vapor. This heat absorption cools the surrounding, like your refrigerator interior. On the TS diagram, it's another horizontal line showing the heat gain. The cycle efficiency is measured by the coefficient of performance or COP, defined as the heat absorbed in the evaporator divided by the compressor's work input. A higher coefficient of performance like 3 or 4 in modern fridge means better efficiency. Analyzing these steps help the engineer to optimize the cooling systems. Next, we will summarize each component's role to solidify our understanding. Now, we will see the key feature of each component. Okay. First, as we have seen, the compressor, its job is to increase the refrigerant pressure and temperature, turning low pressure vapor into high pressure superheated vapor. And this is an isentropic compression, the meaning entropy remains constant, requiring work input like that of engine. Okay. Think of the compressor as the cycle head, pumping energy into the system. Now, in case of the condenser, as it rejects heat to the surrounding, it is like air outside your refrigerator cooling the refrigerant at constant pressure. The superheated vapor condenses in a high pressure liquid, releasing the latent heat. It's like a radiator dissipating heat from a car engine. Third, the expansion valve, which reduces the pressure and temperature through isenthalpic expansion, which means enthalpy remains constant. The high pressure liquid becomes a cold, low pressure liquid vapor mix, which is ready to cool. Now, you can take an example of spraying a mist that instantly chills. It's a quick, efficient drop. Fourth is the evaporator, which absorbs the heat from the surrounding, like your refrigerator interior at a constant pressure. The refrigerant evaporates into low pressure vapor, providing the cooling effect that we are depending. It's the important part of the refrigeration system. For example, in your refrigerator, if you want to make the ice cubes, these evaporators makes it possible. Together, these components create a seamless heat transfer loop. Now here, the table sums up the important role of the different components. The compressor compresses, the condenser rejects the heat, valve expands, and the evaporator absorbs heat. Understanding their thermodynamic roles helps the engineer to design efficient systems like air conditioners with quieter compressor or refrigerator with a good COP. Next, we will see the vapor compression system which is used in the real world. Now, we will see the application of vapor compression cycles in the real world. It is seen everywhere. First, in the refrigeration system. Domestic refrigerator that we use in our house and the freezers which depend on these systems to keep our food fresh. The evaporator chills the refrigerator interior while the condenser dumps the heat which is behind it. In the commercial cold storage that we see in the supermarket, there are the freezers or the warehouses for fruits and vaccines, which uses larger vapor compression systems to preserve goods. Industrial refrigeration, such as in the chemical plants or in the oil refineries, which cools the different process and ensure the safety and efficiency. Now take an example of a refinery which uses a vapor compression refrigeration system to condense gases into liquids. Second, the air conditioning systems, the residential AC units which cool our home by absorbing the indoor heat and releasing it outside. The centralized heating, ventilation, and air conditioning system in our office buildings or hospital uses vapor compression system for climate control, ensuring comfort and air quality. In case of this automotive air conditioner, which are used in the cars, they rely on the compact systems to keep the system cool on the summer days. Third important part is the heat pump. This also uses the vapor compression refrigeration cycle, but in a reverse manner, using the cycle to heat the space in the winter by pulling the heat from the outside air, which is at the low temperature. Imagine a heat pump which is warming our house in the cold weather. Okay, now in the diagram you can see this arrow in the diagram shows the flow of the refrigerant connecting the components to create cooling or heating system. The versatility of this vapor compression system makes it as indispensable across homes, businesses, and industries. That is why we can get a cold environment in summer days and hot room temperature in winter days. Now here, understanding the application of the vapor compression refrigeration cycles impacts the daily life and different industrial process. Now we are going to see the advantages of this cycle. The advantages of the vapor refrigeration cycles is that it is first of all highly efficient. It delivers impressive cooling output for the energy it consumes, which is having a COP between 3 to 4 in the modern systems. For example, a good air conditioner moves 3 times more heat than the electricity it uses, saving money and energy. Second, its compact designs make it perfect for both small and large applications. A refrigerator fits neatly behind the appliance, while the industrial chiller scale up without losing efficiency. This versatility suits everything from room refrigerator to the refrigeration systems of a massive data center. Third is its adaptability to different refrigerants. Engineers can choose different fluids like R134A or R32 based on temperature needs or environmental rules, making the cycle flexible for different climates or regulations. For example, a heat pump in the colder countries such as Russia or Norway might use a different refrigerator than the refrigerator which we are using in India. Fourth is it operates over a wide range of temperature. The temperature in the freezer is at minus 20 degrees centigrade, and the temperature in the room where the air conditioner operates is at 25 degrees centigrade. This makes the vapor compression refrigeration cycle reliable for different tasks. It is also used for keeping the vaccine cold or cooling your car's cabin. These are the advantages which explains why vapor compression refrigeration cycle dominates the refrigeration and heating, ventilation, and air conditioning markets. Okay. Now here, most of the engineers loves this cycle because it balances the performance and practicality. Though it is not a perfect and it is having certain limitations, it is having certain strengths that we appreciate and we are using in the modern cooling. Now we will see certain challenges and the real world inefficiencies which is associated with the vapor compression refrigeration cycle. Now coming on the limitation of vapor compression refrigeration cycle, first is the inefficiency in the real world application, which reduces its performance. Unlike the ideal cycle which we have studied in the above diagram, the real world cycle is actually very different. Okay, because there are problems such as friction, the friction losses in the pipes and in the compressor, and this friction consumes the energy, and due to which the efficiency of the real world or the real vapor compression refrigeration cycle is less as compared to the efficiency of the ideal cycle. Now here the non-isentropic compression means the compressor works harder than it should. Because of this, the COP of the system reduces. Now if in the real world application there is the pressure drop in the condenser and in the evaporator, and this pressure drop reduces the energy of the refrigerant. Okay, it is just like the leaks in the system. For example, a refrigerant can have a COP of 2.5 in real world, but ideally on the paper it can show the COP of 4. Second one, there is the issue of environment is a big concern. Now refrigerants like chlorofluorocarbons and hydrofluorocarbons, which were used in the older systems, okay, were affecting the ozone layer and which contributed global warming. Now in the modern refrigerants, okay, we are not using the CFCs and HFCs, okay, and we have to carefully handle these refrigerants. If there are leakage in the air conditioner, then this could be very much affecting the efficiency. A refrigerant's leaky condition can affect the cooling performance. The third important part is the energy consumption in case of large scale application. The industrial chillers uses a huge amount of electricity for cooling purpose, and this is increasing the electricity cost and also increasing the carbon footprints. For example, if we are cooling a skyscraper with vapor compression refrigeration cycles, it requires a huge amount of power, which is a electrical power, and this causes the engineers to innovate, like designing a tighter seals to reduce the leaks and the high efficient compressor to reduce the energy bills. Now understanding these challenges is very much important to efficiently and properly design the vapor compression refrigeration system. It is it is not enough to build a refrigerator, but it should be built efficiently and eco-friendly. That is the need of the hour. Now these are the important limitations that remind us that the thermodynamics is very much different from the real world constraints. Just like the physics to policy, Now next we will see the environmental considerations and how the different industry or the HVAC industry is tackling with them. Now let's focus on the environment side of vapor compression refrigeration cycle, which is a very hot topic in nowadays world. Historically, refrigerants like CFCs were a disaster. That is, they damage the ozone layer, leading to global bans under the Montreal Protocol. HFC, their replacement are the better for the ozone, but are still contribute to global gas emissions if they leave. Now, the industry is shifting to eco-friendly alternatives like R134A, R290, that is propane, and R32, which have lower global warming potential. For example, R290 is used in some modern refrigerators because it's natural and less harmful. Another focus is improving efficiency to cut energy use. A more efficient vapor compression refrigeration cycle with higher COP reduces electricity demand, lowering carbon emissions from power plants. Think of an air conditioner. If it uses 20% less power, that's a win for your bill and the planet. Innovations like variable speed compressors helping by adjusting the power to match cooling needs, unlike older systems that run at the full speed. Engineers are also designing systems with better leak preventions since even green refrigerants aren't perfect if they escape. For instance, the tighter seals in car AC units keep R134A content. The push for the sustainability is reshaping vapor compression refrigeration cycle, balancing performance with environment responsibility. Now, think of a future where every refrigerator uses natural refrigeration and saves electricity. That's the goal. These efforts tie back to thermodynamics, that is, optimizing heat transfer, reduce waste, aligning with the second law limits. Understanding these considerations shows how engineering tackles global challenges. Next, we will see why vapor compression refrigeration cycle remains vital and what next for this cycle. Now, let's get a summary of today's session on the vapor compression refrigeration cycle. This cycle is a powerhouse driving refrigerants, air conditioning, and heat pumps with remarkable efficiency and adaptability. From keeping your ice cream frozen to cooling entire buildings. The vapor compression refrigeration cycle ability to move heat using a compressor, condenser, expansion valve, and evaporator makes modern life possible. We have explored its thermodynamic heat, that is hot, that is isentropic compression. Then we have seen the constant pressure heat transfer, then isentropic expansion and evaporation. Using the temperature entropy diagrams to visualize the energy flow. The COP metric shows us how effectively it pulls guiding engineer to boost performance. The real-world application like refrigerators, HVAC systems, and car air conditioners highlights its versatility, while advantages like compact design and wide temperature range explain its dominance. But it's not flawless. Frictional losses and energy demands challenge efficiency, and refrigerants pose environmental risks, pushing the shift to the greener options like R290. Further advancement aims to cut cost, improve COP, and adopt sustainable fluids ensuring vapor compression refrigeration cycle stays relevant in a climate conscious world. Think about a heat pump warming a home with minimum energy. That's where we headed. Understanding vapor compression, refrigeration cycle components, and thermodynamics empowers us to optimize systems and tackles issues like emissions, building on concepts. Okay. For homework, sketch a TS diagram for vapor compression refrigeration cycle and label each process. Try calculating the COP for a refrigerator as absorbing 200 kilojoules of heat with 50 kilojoules of compressor work. Now, these lectures have shown how vapor compression refrigeration cycle blends science with practicality, shaping comfort and industry. Thanks for your attention, and I will see you next class to explore more thermodynamic wonders. Thank you.